Hey everyone, welcome back to the channel. If you're preparing for the AI-901 Microsoft Azure AI Fundamentals exam, you're in exactly the right place. In this video, we're diving into a complete crash course that covers all the key concepts you need to pass the exam fast and efficiently. We'll break down topics like artificial intelligence concepts, generative AI and agents, computer vision, NLP, and AI speech concepts, all explained in a simple, easy-to-understand way. And that's not all. You'll also get realistic practice questions to test your knowledge and boost your confidence before exam day. Whether you're a beginner or doing last-minute revision, this video will help you get exam ready. So make sure to hit that like button, subscribe for more certification content, and let's get started. Introduction to AI concepts. Welcome! If you are here, you are probably curious about artificial intelligence, or AI. Maybe you have seen AI in the news, or you are preparing to use it at work or school. This training module offers a high-level overview of the core capabilities of artificial intelligence. You will gain an intuition for how AI works without diving into technical details or writing code. We will not cover the mathematics behind machine learning models, but instead focus on what AI can do and the basic principles that guide it. Whether you are a beginner or just looking to understand AI better, this module is designed for you. Next steps. Let us begin our journey into artificial intelligence, move on to the next unit, and start exploring the fascinating world of AI. What is generative AI? Generative artificial intelligence, or generative AI, is a branch of artificial intelligence that enables software to create new content. This content can include natural language conversations, images, videos, computer code, and more, making generative AI a versatile and powerful technology. How does generative AI work? Generative AI relies on language models that have been trained using massive amounts of data, often sourced from the internet or other public information. Users interact with these models by providing prompts, which are natural language questions or statements. The model then generates a meaningful response by understanding the relationships between words and concepts, allowing it to produce coherent and relevant content. Types of language models. There are large language models, or LLMs, and small language models, or SLMs. LLMs are trained on vast datasets and can handle a wide range of topics, but they require significant resources. SLMs are more focused, making them ideal for specific tasks or for use on local devices. Common uses of generative AI. Generative AI is used to create AI agents that assist users, generate new documents, automate translation between languages, and summarize or explain complex information. These applications help streamline tasks and enhance productivity across many industries. Natural language processing, or NLP, is a field of artificial intelligence focused on helping computers understand and interpret human language. It is the foundation for generative AI large language models, often called LLMs, and powers many modern text analysis solutions. Core text analysis techniques. NLP uses a range of techniques to analyze and summarize natural language text. Language detection identifies which language a document is written in, often as the first step in processing. Text classification assigns documents to categories, including sentiment analysis to determine if the tone is positive, negative, or neutral. Key term extraction and entity detection find important words, phrases, or mentions of people, places, and organizations. A specialized form of entity detection is redacting personally identifiable information, such as names or addresses, to protect privacy. Summarization condenses large volumes of text while preserving the main ideas. Real-world applications. NLP technologies are used to analyze documents, meeting transcripts, and social media posts to identify key topics and sentiment. They also power chatbots that answer common questions and help redact sensitive information to comply with privacy laws. From analyzing opinions to protecting privacy, NLP is essential for making sense of language in today's digital world. Speech capabilities in artificial intelligence applications and agents are transforming how people interact with technology. By enabling communication through spoken language, these systems make digital experiences more natural and accessible for everyone. Core speech technologies. At the heart of these capabilities are two key technologies. First, speech recognition allows artificial intelligence to hear and interpret speech, typically by converting spoken words into written text through speech-to-text systems. Second, speech synthesis gives artificial intelligence the power to vocalize words as spoken language, using text-to-speech technology to turn written information into audible speech. Advancements in AI speech. Artificial intelligence speech technology is advancing rapidly. Modern systems are learning to ignore background noise, detect interruptions, and generate voices that sound increasingly expressive and human-like. These improvements are making interactions with artificial intelligences smoother and more engaging. Real-world applications. Common uses of artificial intelligence speech technologies include agents that understand spoken commands, automated transcription of calls or meetings, audio descriptions for videos or text, and automated speech translation between languages. Computer vision is a branch of artificial intelligence focused on analyzing visual input, such as photographs, videos, and live camera feeds. By teaching computers to interpret images, computer vision enables machines to understand and interact with the visual world. How computer vision works. Computer vision relies on training models with vast numbers of images. These models learn to recognize patterns, objects, and features by analyzing labeled examples. Once trained, they can interpret new, unlabeled images and make predictions about what they see. Types of computer vision models. There are several types of computer vision models. Image classification models identify the main subject in an image. Object detection models go further, pinpointing the location of specific objects. Semantic segmentation is even more advanced, identifying the exact pixels that belong to each object. Multimodal models combine visual features with text descriptions, allowing them to generate detailed descriptions of images. Real-world applications. Computer vision powers many everyday technologies. It enables artificial intelligence agents to interpret visual input, generates captions or tags for photos, and supports visual search. In retail, it helps monitor stock levels and identify items at checkout. Computer vision is also used in security video monitoring, facial recognition for authentication, robotics, and self-driving vehicles. Artificial intelligence is transforming the way we handle information by automating information extraction from unstructured data sources. Whether it is scanned documents, forms, images, or even audio and video recordings, AI can find valuable information and unlock insights that were previously hidden. How information extraction works. At the core of most document analysis solutions is a computer vision technology called optical character recognition, or OCR. OCR identifies the location of text within an image, making it possible to digitize printed or handwritten content. But OCR is just the beginning. It is often paired with analytical models that interpret individual values, allowing the extraction of specific fields. For example, matching text from a receipt to fields in an expense claim submission. Expanding beyond text. While traditional data extraction models focused on text-based forms, advancements in AI now enable extraction from audio recordings, images, and videos. These more sophisticated models are becoming increasingly accessible, broadening the scope of what can be analyzed and understood. Common use cases. AI-powered information extraction is used for automated processing of business documents, large-scale digitization of paper forms like census records, indexing documents for search, and identifying key points or follow-up actions from meeting transcripts or recordings. Responsible AI means building artificial intelligence systems with safeguards to prevent harmful, illegal, or offensive outcomes. It is about ensuring that AI technologies are developed and used in ways that are ethical, safe, and beneficial for everyone. Principles of responsible AI. There are several key principles behind responsible AI. Fairness is crucial, as AI models can inherit biases from the data they are trained on. Developers must minimize these biases to avoid discrimination. Reliability and safety are also essential, since AI is not perfect and can make mistakes. Privacy and security matter too, because personal data must be protected throughout the AI lifecycle. Inclusiveness ensures that AI solutions are accessible to all users, not just a select few. Transparency helps users understand how AI works and its limitations. Finally, accountability means organizations must take responsibility for their AI systems and apply strong governance frameworks. Real-world examples. For example, a college admissions AI should be tested for fairness to avoid bias. A robotic system should only act when it is confident in its object detection. Facial recognition at airports must delete images after use. AI agents should provide captions for accessibility, and banks must disclose how AI is used in loan decisions. Responsible AI is about building trust, protecting people, and ensuring technology works for everyone. Question 1. Which is the most accurate description of generative AI? A. Generative AI uses a language model to create original content in response to a prompt. B. Generative AI is an older form of AI that's superseded by machine learning. C. Generative AI is a complex form of AI that can only be used by specialists such as data scientists. The correct answer is option A. Question 2. What is an AI agent? A. A technology professional who builds AI applications. B. Anyone who uses AI applications. C. An AI application that can perform tasks on behalf of a user. The correct answer is option C. Question 3. An AI application reads email aloud to a user. Which AI speech capability is being used? A. Speech recognition. B. Speech synthesis. C. Sentiment analysis. The correct answer is option B. Introduction to Generative AI and Agents. Generative artificial intelligence, or generative AI, is quickly becoming a familiar term, even for those outside the world of technology. Its ability to create original content that feels remarkably human has captured the imagination of people everywhere. The magic of generative AI. Futurist and novelist Arthur C. Clarke once said, "Any sufficiently advanced technology is indistinguishable from magic," said Arthur C. Clarke. Generative AI certainly fits this description, producing poetry, stories, and even computer code that can seem almost miraculous. But behind the scenes, there is no actual wizardry at work. Instead, generative AI relies on years of research in statistics, data science, and machine learning to achieve these impressive results. How generative AI works. At its core, generative AI uses mathematical techniques to analyze vast amounts of data, learning patterns and structures that allow it to generate new, original content. These methods have been incrementally discovered and refined over time, making today's AI agents more capable than ever before. By understanding these core concepts, anyone can begin to see how the magic trick is performed. Looking to the future. As generative AI continues to evolve, learning about its principles empowers us to imagine new possibilities for tomorrow's technology. Large language models, or LLMs, are at the heart of generative artificial intelligence. These models, along with their smaller counterparts called small language models, capture the complex relationships between words and phrases, allowing them to understand and generate meaningful language. How large language models predict language. LLMs are trained to generate completions based on prompts, much like an advanced version of predictive text on your cell phone. When given a prompt, the model predicts the most likely next word by analyzing which words in the sequence are most influential, ensuring the response is both relevant and coherent. The role of tokens. Instead of thinking in terms of whole words, LLMs use tokens. Tokens can be entire words, subwords like in unbelievable, punctuation, or other common character sequences. This approach allows the model to handle a vast vocabulary, often consisting of hundreds of thousands of tokens. Training with tokens. Training begins by breaking down massive amounts of text into these tokens, each assigned a unique identifier. As more data is added, the vocabulary grows, enabling the model to recognize and generate a wide range of language, from simple words to complex phrases. Transformers are powerful models that help computers understand language by relating words or tokens to each other. But how does this actually work? Let's break it down. Token embeddings and attention. First, each token is assigned a unique vector, which is just a list of numbers. These vectors start out random, but they're transformed into embeddings that capture the meaning and context of each token. To do this, transformers use a technique called attention. Attention looks at each token and weighs how much nearby tokens influence its meaning. For example, in the phrase, "I heard a dog bark," the words dog and heard are more important for understanding bark than I or a. Encoder and decoder blocks. A transformer has two main parts, the encoder and the decoder. The encoder uses attention to create embeddings, while the decoder uses those embeddings to predict what comes next in a sequence. Multi-head attention lets the model consider different aspects of meaning at once, making the process efficient. Predicting the next token. When given a prompt, the decoder predicts the next most likely token, one at a time, using attention and a neural network. This process repeats until the sequence is complete. A prompt is simply the input you give to a large language model, or LLM, to get a response. It could be a question, a command, or even a casual comment to start a conversation. The model replies with what's called a completion. Types of prompts. There are two main types of prompts. System prompts set the behavior, tone, and constraints for the model. For example, you might tell the model to act as a helpful assistant with a friendly manner. User prompts, on the other hand, are specific questions or instructions from the user, like asking for a summary or a list. Conversation history. Generative AI applications often keep track of conversation history. By including previous prompts and responses, the model maintains context, making its answers more relevant and consistent as the conversation continues. Retrieval augmented generation. Retrieval augmented generation, or RAG, adds even more context. The application retrieves relevant documents or data, then includes that information in the prompt. This helps the model give answers grounded in real, specific information. Tips for better prompts. To get the best results, be clear and specific, add context, provide examples, and ask for structured responses. Well-designed prompts make a huge difference in the quality of generative AI outputs. Imagine a digital assistant that does more than just answer your questions. Welcome to the world of AI agents. These are software applications powered by generative artificial intelligence designed to reason, generate natural language, and automate tasks in real time. Components of an AI agent. Every AI agent is built from three essential elements. First, there is a large language model, which acts as the agent's brain, enabling it to understand and reason with language. Second, instructions, known as system prompts, define the agent's role and behavior, much like a job description. Third, tools allow the agent to interact with the world, making it capable of more than just conversation. Tools and capabilities. AI agents use knowledge tools, such as search engines or databases, to access information. They also have action tools that let them perform tasks like sending emails, updating calendars, or even controlling devices. With these abilities, AI agents can automate tasks and collaborate with you to boost efficiency. Multi-agent systems. AI agents can also work together in multi-agent systems. Each agent specializes in a task, collaborating through prompts to complete complex workflows, much like a human team. The future of agentic AI. Agentic AI is poised to transform how we find information and get work done, making technology smarter and more collaborative than ever. Question 1. What is a large language model, LLM? A. A type of AI model designed to generate human-like text. B. A model that only processes images, not text. C. A small, efficient model for mobile devices. The correct answer is option A.
Question 2. What is the purpose of tokenization? A. To sort the words in a sentence alphabetically. B. To break down text into smaller units. C. To convert text into binary code for processing by computers.
The correct answer is option B. Question 3. What are embeddings? A.
Extra words added by a transformer model to enhance text generation. B. Small language models used for specific tasks. C. Vector-based representations of tokens that capture their semantic meaning.
The correct answer is option C.
Question 4. What does an attention layer do in a transformer model? A. Removes irrelevant words from the input text. B. Examines the relationships between each token and the tokens around it. C. Flags inappropriate content in the generated text.
The correct answer is option B.
Question 5. What is the purpose of a system prompt? A. To provide context and instructions to the AI model. B. To configure a generative AI model to run on a particular operating system. C. To store user preferences for future interactions.
The correct answer is option A.
Question 6. What is an agent in the context of AI? A. An AI system that can perform tasks on behalf of a user. B. A generative AI model that operates in secret. A human operator to whom generative AI models escalate requests they can't handle.
The correct answer is option A.
Introduction to Natural Language Processing Concepts. Text tokenization is the process of breaking down a body of text, or corpus, into smaller pieces called tokens. Typically, each distinct word becomes a token, but tokens can also include partial words or combinations with punctuation. Tokenization example. Take the phrase, "We choose to go to the moon." Each word is a token. We choose to go to the moon. Notice "to" appears twice, showing how tokens can repeat. Why tokenization matters. Assigning discrete values to tokens allows us to count their frequency. This helps identify the most commonly used terms and can reveal the main subject of the text. Pre-processing techniques overview. Before tokenization, several pre-processing techniques can be applied to improve analysis, depending on your goals. These include text normalization, stop word removal, n-gram extraction, stumming, and lemmatization. Text normalization. Text normalization involves removing punctuation and converting words to lowercase. While this improves performance, it may lose some semantic meaning. Stop word removal. Stop words like the or it are excluded to focus on more meaningful words, making analysis more effective. N-gram extraction. N-gram extraction identifies multi-word phrases, such as artificial intelligence, to better capture important concepts. Stemming and lemmatization. Stemming strips word endings, while lemmatization reduces words to their dictionary form, ensuring accurate analysis. When analyzing large collections of text, or corpora, statistical techniques help uncover meaning and structure. Let's explore 4 essential methods: frequency analysis, term frequency inverse document frequency, bag of words for machine learning, and text rank summarization. Frequency analysis. Frequency analysis is the simplest approach. By counting how often each word appears, you can quickly identify the main topics. For example, if AI and business are the most frequent terms, the document likely discusses artificial intelligence in business contexts. TF-IDF. Term frequency inverse document frequency, or TF-IDF, refines this by highlighting words that are common in one document but rare across the entire corpus. This helps distinguish what makes each document unique. For instance, Copilot might stand out in one document, while Foundry is unique to another. Bag of words and machine learning. The bag of words technique represents text as word frequency vectors, ignoring grammar and order. This is the foundation for machine learning models like naive Bayes, which can classify emails as spam or not, or perform sentiment analysis. Text rank summarization. Text rank is a graph-based algorithm that summarizes text by ranking sentences based on their similarity. The highest ranked sentences form a concise summary, capturing the document's key points efficiently.
Modern language models use vectors or multidimensional arrays of numbers to represent words and their meanings. This approach, known as embeddings, allows models to capture the semantic relationships between words, making text analysis more powerful and efficient. How vectors represent meaning. Each word is mapped to a point in multidimensional space. Words with similar meanings, like dog and cat, have vectors that point in similar directions. For example, dog might be represented as 0.8, 0.6, 0.1, while cat is 0.7, 0.5, 0.2. Their closeness reflects their semantic similarity. Comparing words with cosine similarity. To measure how similar two words are, models use cosine similarity. For instance, dog and cat have a high similarity score of 0.992, while dog and tree score much lower at 0.333. This helps identify which words are most alike or the odd one out. Vector arithmetic and analyses. Vector arithmetic lets us perform operations like dog plus young equals puppy. Similarly, kitten minus puppy plus dog results in cat. These calculations reveal deep linguistic relationships and analogies. Applications in text analysis. Vector-based models power tasks like summarization, keyword extraction, named entity recognition, and text classification. By leveraging semantic similarities, these models efficiently analyze and organize language, forming the backbone of modern natural language processing.
Question 1. What is the purpose of tokenization? A. To translate text into another language. B. To summarize large documents. C. To break down text into smaller units for analysis.
The correct answer is option C.
Question 2. Which of the following techniques is used to determine the importance of words in a specific document within the context of a larger collection of documents? A. Naive Bayes. B. TF-IDF, term frequency inverse document frequency. C. Word to vec.
The correct answer is option B.
Question 3. Which of the following best describes the role of embedding vectors in natural language processing, or NLP? A. They duplicate tokens in multiple languages. B. They define stop words that should be ignored. C. They capture semantic token relationships in multiple dimensions.
The correct answer is option C.
Introduction to AI speech concepts. Speech is one of the most natural ways humans communicate, making it a powerful tool for artificial intelligence applications. Integrating speech capabilities into AI creates more intuitive, accessible, and engaging experiences for users, whether in daily tasks or specialized applications. Core capabilities: recognition and synthesis. There are two fundamental speech technologies at the heart of voice-enabled applications. Speech recognition converts spoken words into text, allowing AI to understand and process what users say. Speech synthesis, on the other hand, transforms written text into natural-sounding speech, enabling AI to respond in a human-like voice. Together, these technologies enable seamless conversational interactions between people and machines. Real-world impact. From voice assistants to accessible applications and conversational AI agents, speech technologies are essential for modern AI solutions. Understanding how these capabilities work can help developers create transformative user experiences across a wide range of real-world scenarios. Speech recognition is transforming how we interact with artificial intelligence applications. By combining speech recognition, which converts spoken words into text, and speech synthesis, which generates natural-sounding audio from text, these technologies enable hands-free operation, improve accessibility, and create more natural conversations. Speech recognition in action. Speech recognition, also known as speech-to-text, powers a wide range of applications. In customer service, it transcribes calls in real time, routes callers, and analyzes sentiment. Virtual assistants accept voice commands, answer questions, and control smart devices. In healthcare, clinicians dictate patient notes directly into electronic health records, reducing administrative burden and improving documentation accuracy. Speech synthesis in action. Speech synthesis, or text-to-speech, brings written content to life. AI agents respond with natural voices, making interactions more engaging. Applications read web content aloud for users with visual impairments or reading disabilities. Educational platforms create narrated lessons, while entertainment creators generate character voices and voiceovers for games and videos. Combining speech capabilities. The most powerful experiences combine both technologies. Voice-driven customer service agents listen and respond conversationally. Interactive voice response systems guide callers naturally. Language learning apps provide spoken feedback, and voice-controlled vehicles enable hands-free operation and updates. Key considerations. Before implementing speech, consider audio quality, language support, privacy, latency, and accessibility standards to ensure an inclusive and effective user experience. Speech recognition starts with a microphone, turning sound waves into digital signals. These signals are sampled thousands of times per second, often at 16,000 samples per second, to capture every detail of your voice. Feature extraction. Next, the system cleans up the audio, removing background noise. It then transforms the raw sound into a compact form using mel-frequency cepstral coefficients, or MFCCs. This process highlights the most important speech features, making it easier for the system to understand. Acoustic modeling. Now, deep learning models called transformers analyze these features. They predict phonemes, which are the smallest units of sound in language. For example, the word cat is made up of 3 phonemes, k, a, and t. But recognizing sounds is not enough. Language models step in, using grammar and vocabulary knowledge to predict which words make sense together. This helps the system choose between words like there and there. Decoding. Decoding algorithms then search through possible word combinations, balancing what was heard with what makes sense to select the most accurate transcription. Post-processing. Finally, post-processing polishes the text, adding punctuation, capitalization, and formatting numbers, ensuring the output is clear and readable. That is how speech becomes text. Speech synthesis, also known as text-to-speech, or TTS, transforms written words into lifelike spoken audio. You hear it when your phone reads notifications, navigation apps announce directions, or accessibility tools narrate text aloud. Text normalization. The first step is text normalization. This stage prepares raw text for speech by expanding abbreviations, numbers, and symbols into their spoken forms. For example, Dr. Smith ordered 3 items for $25.50 on 12/15/2023 becomes Dr. Smith ordered 3 items for $25.50 on December 15th, 2023. This ensures the system produces natural, understandable speech. Linguistic analysis and G2P. Next, linguistic analysis breaks the normalized text into phonemes, the smallest units of sound. Grapheme to phoneme, or G2P, conversion maps letters to sounds, handling tricky English spellings like though, through, and cough. Neural networks help manage unknown words and context, ensuring accurate pronunciation. Prosody gives speech its rhythm, stress, and intonation. Transformer neural networks predict how to say each word, adjusting pitch, duration, and emphasis. This makes speech sound expressive, not robotic, and helps listeners understand meaning and emotion. Waveform generation. Finally, neural vocoders like WaveNet generate the audio waveform, turning phonemes and prosody into clear, natural-sounding speech. The result is high-quality audio produced in real time.
That is how speech synthesis brings text to life, one word at a time.
Question 1. What activity happens during the pre-processing stage of speech recognition? The audio is converted to .wmv format. Background noise is added to the audio signal. Feature vectors are extracted from the audio waveform for modeling.
The correct answer is option C. Question 2. What are phonemes?
Artifacts that are removed from the signal as part of the cleanup process. The smallest unit of sound in speech. AI models that generate audio.
The correct answer is option B. Question 3. Why is it important to generate prosody in speech synthesis? Prosody maximizes the volume of the audio output. Prosody translates the speech to the language of the listener. Prosody ensures natural pronunciation and speech cadence. The correct answer is option C.
Introduction to computer vision concepts.
Computer vision is a fundamental area of artificial intelligence, or AI, focused on enabling machines to process and understand visual information. Unlike humans, computers do not have biological eyes, but they can analyze images from cameras, photographs, or videos. Real-world applications. Think about an autonomous vehicle navigating city streets. It must detect traffic signals, recognize pedestrians, and respond to obstacles. Or consider a store using smart checkouts, where cameras identify the products in a customer's basket. Even a doorbell camera that detects people at your front door relies on computer vision. These examples show how computer vision powers everyday technology, making our lives safer and more convenient. How computer vision works. The key to computer vision is processing images in a way that emulates human visual perception. By analyzing visual data, AI applications can interpret and respond to their environment, whether it is a live camera feed or a digital photograph. In this module, we will explore the essential building blocks behind modern computer vision solutions. Computer vision is a branch of artificial intelligence that enables computers to process and understand visual information from images, videos, or live camera feeds. Over the years, computer vision techniques have evolved, allowing machines to interpret the world visually, much like humans do. Key techniques: image classification and object detection. One foundational technique is image classification. Here, a model is trained with thousands of labeled images to predict what's in a new image. For example, in a grocery store, a smart checkout system could identify apples, oranges, or bananas placed on a scale, charging customers automatically. For more complex scenarios, object detection is used. This method scans an image for multiple items, identifying each object and its location using rectangular bounding boxes. Advanced methods: semantic segmentation and contextual analysis. Semantic segmentation takes things further by classifying every pixel in an image, offering a highly detailed understanding of object locations. The latest multimodal models go beyond objects, analyzing relationships between items and the text that describes them, enabling computers to generate descriptions or suggest relevant tags. Real-world example and impact. Imagine a system recognizing not just an apple, but also a person eating it. Computer vision is transforming industries, making everyday tasks smarter and more efficient. To a computer, an image is just an array of numbers. Each number represents a pixel, with values ranging from 0 for black to 255 for white. For example, a 7x7 grid of numbers forms a simple grayscale image. Color images and channels.
Most digital images are not just grayscale. They use 3 layers, called channels, to represent red, green, and blue colors. This is known as the RGB model. By combining different values in each channel, computers can display millions of colors. What are filters? Filters are a powerful tool in image processing. A filter uses a small array of numbers, called a kernel, to modify pixel values and create visual effects. For example, a 3x3 kernel can highlight edges or blur an image. How filtering works. The filter kernel is moved across the image, multiplying its values with the underlying pixels and summing the results. This process is called convolution. Sometimes the resulting values are outside the normal range, so they are adjusted to fit between 0 and 255. Effects of filters. Different filters can sharpen, blur, or even invert colors in an image. The Laplace filter, for example, highlights the edges of objects, making shapes stand out more clearly. Filters are essential for many image editing and computer vision tasks.
Convolutional neural networks, or CNNs, are a powerful deep learning architecture used in computer vision. Unlike traditional image filters that simply apply effects, CNNs are designed to extract meaningful features from images to help machines understand what they see. How CNNs process images. CNNs use layers of filters, also called kernels, to scan images and generate numeric feature maps. These feature maps highlight important visual patterns, like edges or textures. As images pass through multiple filter layers, the network captures increasingly complex features. The resulting feature maps are then flattened into a single array of numbers, which represent the essential characteristics of the image. Training a CNN. During training, CNNs start with randomly assigned filter weights. Images with known labels, such as apples, bananas, or oranges, are fed into the network. The model predicts a label, and its output is compared to the actual label. The difference, called loss, is used to adjust the filter and network weights. This process repeats over many epochs, gradually improving accuracy. Using the trained model. Once trained, the CNN uses its learned weights to predict labels for new, unlabeled images. This enables the model to classify images based on the features it has learned to recognize. Convolutional neural networks, or CNNs, have long been the backbone of computer vision. They excel at tasks like image classification and object detection by extracting features from images and identifying regions of interest, driving many advances in visual AI. Transformers in NLP. In natural language processing, or NLP, a different architecture called the transformer has revolutionized language models. Transformers process vast amounts of text, encoding words or phrases as vectors using a technique called attention. This creates embeddings that capture the context and relationships between words. Vision transformers. Inspired by their success in language, researchers developed vision transformers, or VITs, for image data. Instead of words, VITs break images into patches, generating vectors based on visual features like color, shape, and texture. Attention mechanisms then map contextual relationships between these patches. Multimodal models. When images are paired with text, both language and vision transformers can be combined into multimodal models. Using cross-modal attention, these models create unified representations, linking visual features with language and enabling complex image descriptions, even for images never seen before. Summary. CNNs, transformers, and multimodal models each play a unique role in AI, advancing our ability to understand images, language, and their connections, powering everything from object detection to sophisticated image captioning. Artificial intelligence can now create images and videos from simple text prompts thanks to advanced multimodal model architectures. These models understand both language and visuals, allowing them to generate detailed pictures or even moving scenes based on a written description. How diffusion models work. Most modern image generation models use a process called diffusion. Here's how it works. The model starts with a random set of pixel values, essentially visual noise. Using the text prompt, such as a dog carrying a stick in its mouth, the model identifies visual features that match the description. Through multiple iterations, the model gradually removes noise and adds structure, refining the image step by step. After each round, it checks how closely the image matches the prompt, repeating this process until the final, detailed image is produced. From images to video, adding motion and logic. Some models extend this approach to video generation. They use the same diffusion technique, but add extra layers of complexity. The model considers how objects behave in the real world, like making sure a dog's feet stay on the ground, and ensures the video unfolds in a logical sequence. AI image and video generation is transforming creativity, using language and visual understanding to bring ideas to life, one prompt at a time.
Question 1. Computer vision is based on the manipulation and analysis of what kinds of values in an image? Timestamps and photograph metadata? Pixels? Image file names?
The correct answer is option B. Question 2. What is the primary role of filters in a convolutional neural network CNN used for image classification? To apply visual effects to enhance image appearance, to extract numeric features from images for use in a neural network, to compress image size for faster processing. The correct answer is option B. Question 3. Which description best matches a vision transformer, VIT? A tool that applies filters to images, changing their visual appearance. An AI agent that converts a large language model to a vision model. A model that uses attention to process image patches and create contextual embeddings. The correct answer is option C.